Welcome everyone. Are you ready for some aldehyde and ketone reactions? Because oh boy, we got a doozy for you today. Let's take a look at Key Concepts Unit 2, Part 3. We saw the first one of these nucleophilic addition reactions in the previous video. But we're going to take a look at it again just to remind ourselves of what the mechanism was, because if we know the mechanism for the hydration reaction, we use that to understand some mechanisms of some other reactions. Okay, so hopefully you found your key concepts. Scroll down until you see, oh, I added this in so I wouldn't forget. I clipped it out, yes. Okay, so we're right before synthesis of cyanohydrins. And it's a section right before cyanohydrins and right after hydration. So let's review that. Okay, hydration. Okay, so there's two routes. Let's call it A and B. Acid, it'll be step A, and B will be a step base. Okay, so the hydrate means add water, right? Make sure you're hydrating yourself every day. It's important for good health to drink lots of water. And these hydration reactions work for either aldehydes or ketones. So let's show an aldehyde here. And we'll show a ketone here. And we're going to hydrate it. And you simply add water. And you can either add acid or you can do base. So base hydroxide ion or NaOH or your favorite alkali metal, sodium, potassium, lithium, whatever. And what happens is where the carbon is double bonded to oxygen, now you have two oxygens. So where the carbon was double bonded to oxygen, now there's two oxygens. And for hydration, they're both alcohols. And oh boy, I didn't give myself much room. We can squeeze in here the ketone, split it, split the double bond O into two O's, single bonded, make them both alcohols. Do the same thing down here, get the same exact products. The mechanism, however, is different. Get the same products. Cool. Acid catalyzed, base catalyzed. Let's see the difference in the mechanism. And I still want to have these important pieces here. So why don't I do a quick delete here? Oh, one more thing before I delete. I think for this video, just to simplify things and allow you to compare and contrast between or among the reactions, let's do the reactions today using, I was going to say ketone, a specific ketone. Let's use acetone, because if you know the mechanism for acetone, simply change one of the carbons to a hydrogen, and then you know the mechanism for the aldehyde. Sweet. All right, let's take care of all this right here. Good. Okay, let's see the mechanism. And I forgot to switch back to the pen mode. So you saw this in a previous video. We talked about the reaction and the mechanism in more detail. So take a look at that if you need a refresher. If this is too fast, yeah, go back and just fast forward to the end of the previous video. The way it works with either an aldehyde or ketone, but I'm going to stick with acetone. Well, if you have an acid, you could use hydronium ion, or you could use H plus and water, or you could specify sulfuric acid mixed with water, whatever. I got hydronium here. Step one, hey, strong acid, do your thing. Donate H plus, give it to the lone pair of the oxygen. Hydronium turns into water. Cool, first step's done, the acid-base step's done. And then the lone pair on your nucleophile. Water is a weak nucleophile. You might remember that from SN2 reactions. We talked about strength of nucleophiles. Stronger nucleophiles have negative charges. This one's neutral. Lone pair on the oxygen, though, even though it's a weak nucleophile, this oxygen is positive. That activates this ketone towards an attack, a nucleophilic attack. And then we bump up the pi bond. The pi electrons move up on the oxygen. So this oxygen that was positive goes back to being neutral. And it gets us 2 lone pairs. And it no longer has 3 bonds. It only has 2. So that's quite stabilizing. The incoming nucleophile hangs on to those hydrogens initially. So the incoming oxygen then has a positive charge because it's making 3 bonds. And then you have to remember to bring in another water molecule, right? Hydronium ion. That's not exactly what we have in a bottle in the lab. It's a mixture of acid and water. So there's plenty of water around. So go grab another water molecule and now use it as a base to remove the extra hydrogen. And then squeeze it in here. You get your diol. 2 alcohols on the same carbon. And the water molecule picks up H+, and you reform the catalyst. Started with hydronium ion, and you end with it. Didn't use it up, sped up the reaction. That makes it a catalyst. Do the same thing under base catalyzed conditions by mixing sodium hydroxide and water. And now hydroxide ion is a negatively charged oxygen. It's a good nucleophile, so it immediately attacks the carbonyl in this base catalyzed mechanism. Same pattern, though, we saw in the second step of acid catalyzed, right? Nucleophile bumped up the pi bond. Down here in base catalyzed, that's our first step. Nucleophile bumps up the pi bond. Incoming nucleophile attaches, we're good. Bring in a water molecule. We had to do that over here to kind of clean up. And, finish off the reaction. Lone pair on this negatively charged oxygen picks up an H+ from water. And we get our diol. Same product. Not well drawn. Oh, I'm going to leave it. I won't be a perfectionist. And the hydroxide ion is reformed from the water molecule. Yay, start with hydroxide and with hydroxide. Okay, so those are the 2 mechanisms we discussed in the previous video. Understand them as well as memorize them. And something to keep us straight as you're making all these curved arrows and drawing your intermediates. You know, the intermediates are short-lived products. They're all the molecules that possess carbon, but they're not final products yet. This is an intermediate, that's an intermediate. If it's an acid catalyzed mechanism, remember you have H+. So your intermediates, it should in general, the good guideline, not a hard and fast rule, a good guideline is that all your intermediates then should be either positive or neutral. So let's check that. For the acid catalyzed route, first molecule is neutral, second intermediate is positive, third intermediate is positive, last molecule product is neutral. All right, it's following the pattern. If we're doing the base catalyzed mechanism, we're using lots of O-. It could be a different base, but bases generally are negative, they're anions. And so in that case, if you have a base catalyzed mechanism, your intermediate should either be negative or neutral. So let's double check. The acetone is neutral. First intermediate is negative. Final product's neutral again. Good. There will be exceptions. I got one for you in this video. Starts out, what is the mechanism? Starts out acid catalyzed, and wait, we're getting an anion and a cation in one of the intermediates. So what's going on there? Oh, nature, she's breaking her own rules. No, she's making the rules, and we're trying to figure them out. So I made up this rule, and it's not a very, very good rule. Nature likes to break these rules, but it's still a good guideline, right? Something to keep in mind, help us steer straight. So if you start mixing up the 2 mechanisms, this is one way to steer yourself straight. Try and get all your pluses in one mechanism, all the negatives in another. Hope that's helpful. All right, let's look at the first of several reactions of aldehydes and ketones. These are nucleophilic addition reactions. Nucleophilic addition reactions. There's a 2 here because number 1 is hydration. And we just saw the mechanism up above. Okay. Synthesis of something called a cyano. Do I have that broken down here? No. Okay, cyano is the IUPAC prefix for the nitrile functional group, a carbon-nitrogen triple bond functional group. That's called a nitrile, but if you name molecules containing the nitrile group, and when they're not the most important functional group, the prefix is cyano. Hydrin, well, that sounds like hydrate. It's a reference to water, specifically an alcohol group. There's a connection there. It's not perfect. Anyways, cyano, C triple bond N, hydrin, an OH group. Well, that's what we're going to do. Let's take acetone and make it into a cyanohydrin. What used to be double bonded O becomes this alcohol group, and you're going to add the nitrile group. That's the product. Okay, what are the reagents? Well, if you look at what you start with and what you end up with, you had to add an H and a CN. Those are the reagents. So on the exam, if you just give me HCN, full credit. In the lab, however, to make it speed up, oftentimes we add a little amount of cyanide ion. It acts as a catalyst. So you might see KCN with HCN, or just NaCN with HCN. Or you might just see HCN, hydrogen cyanide. Oh, cyanide, highly toxic. So if we go back to lab, no, we're not going to be doing this reaction, just for safety purposes. But if you go into industry or if you go into graduate school, it's actually a quite useful reaction. Last bullet point here. For synthesis, I'll put in parentheses because we're not covering it today. You can take the cyanohydrin and you can change it into a carboxylic acid. You can also change it, well, it's got a nitrogen, you can also change it into an amine. Okay, so you start with one functional group, a ketone, or an aldehyde, right? Nice trick there. At an H now, it starts from an aldehyde. And you get 2 functional groups, alcohol, nitrile. And then you can take that and make, have 2 different, different functional groups, alcohol and the carboxylic acid, alcohol, nitrile. You can actually change this into other functional groups. This alcohol can form an alkene if you dehydrate it with POCl3 and pyridine, or anyways, enough of that. Getting off base here. Let's talk about, it's time for the mechanism? Not yet. Reversible, nope. How about we interrupt this message for an important word from our advertiser? I don't know, I'm trying to be silly, trying to be entertaining. But let's get real. Why do we focus on something as weird as a cyanohydrin? Synthesis is one reason, but nature's another reason. So here, on Canvas, I have this. You can read it at your leisure. But this poisonous millipede actually creates this cyanohydrin, mandeleonitrin, maybe. I'm not sure how to say that. Mandeleonitrile. Anyway, stores that, and then it converts it, reverses the reaction, right? So we've been focusing on how to make that. Well, I'll start with an aldehyde. Well, here's benzaldehyde, HCN, and that converts it to a cyanohydrin. So this bug does that in its body somewhere, accumulates a bunch of this, puts it in this gland, and then quickly converts it, hydrolyzes it, in fact, to revert back to initial products, initial reactants, a lot of toxic hydrogen cyanide, and it sprays it at its enemy. Interesting. Stay away from that bug. Okay, let's see the mechanism. Yeah. Okay, mechanism. Let's start with acetone. And write a little HCN. Well, HCN is a weak acid, right? It's leading with an H in the chemical formula, just like HCl. And how'd you guys draw it before? Did you draw it like that? Or did you draw it like this? Sorry. Yeah, what am I doing? I'm trying to think of acetic acid, and that's not how you do it. There's another one there. Yeah, forget that one. This might maybe look a little better. There we go. That's the acetate ion. Here's an H leading first. H leading first. It identifies it as an acid. It's not one of the strong ones you had to memorize from Gen Chem, so it must be weak. So it exists in equilibrium, releasing a little H plus, a little cyanide, goes back and forth. So in the absence of a catalyst, if you just put in HCN all by itself, before the mechanism begins, some of the HCN falls apart to produce some of the cyanide ion. And it turns out that's your nucleophile. And it's a base catalyzed mechanism. So I put that in parentheses because you don't have to identify as such. But if you realize the first step of cyanohydrin reactions takes something that has an anion in it, then you can go back up here and say, wait, we have a base catalyzed mechanism. There's anions. We should have negative or neutral. Hey, does it follow this pattern? Nucleophile with something negative charge, bump up the pi bond. Next step, lone pair of that negative intermediate, go grab an H plus from somewhere and end up with product. Yeah, patterns. So what's the pattern? You got a good nucleophile. Cyanide actually showed up in SN2 reactions as a good nucleophile. It attacks immediately, bumps up the pi bond. Oh, sorry, let's not draw it that way. I'm a visual learner. So the oxygen becomes negatively charged. The nitrile, I got my curved arrow pointing from the bottom, so you don't have to draw it on the bottom, but it makes sense to me. And then now we got a negative charged oxygen. We need an H plus from somebody, but all we have in the reaction is hydrogen cyanide. But that'll work. It's a weak acid, just like water was a weak acid in hydration reaction. Our first nucleophilic addition reaction. And we formed the cyanohydrin, and we reformed the catalyst. So we didn't use up any cyanide ion. There's no net change. Cool. Nice. Done with the mechanism. A lot of these nucleophilic addition reactions, including hydration, including cyanohydrin formation, they are reversible. That's our second bullet point here. So we just mentioned that millipede, it's exploiting that fact. It made the cyanohydrin, and then when it gets bothered or it's in a defensive mode, it quickly converts it back to hydrogen cyanide and squirts it at its enemy. So that's a reversal of the whole mechanism. So you need to be able to do that too. There's two ways of doing it. So if I say, hey, start with the cyanohydrin and reverse it or hydrolyze it, that'll be the key word to go backwards in your mechanism. How much room do I got? Oh, I got plenty of room. Cool. Let's keep this up here. Two ways of doing it. One way, brute force. Okay. Let me just, before I get into the details, let's just make the note, reaction is reversible. Exclamation point. That means if you have the cyanohydrin, it can go backwards to convert it to its initial starting material, the ketone, plus HCN. in the lab, you can just attach a vacuum pump to a container of this molecule, and it's in equilibrium here at creating some of the hydrogen cyanide gas. So under vacuum, you can remove it. So in the lab, that might be the way you do it. An easier way to do it, and a common way of hydrolyzing our reactions in this Unit 2 video is simply that hydronium ion. So that's the reagent. But it's going to have a different mechanism. It's going to be a combination of hydration and the cyanohydrin formation. I'm not going to require that you know that one. It gives you the same product, the ketone. And if you really want to know, we can talk about it. Email me. I can send you information about the reverse reaction using hydronium to get to the ketone. It's a longer mechanism, but you know what? You don't have to know that one. You only have to know this one backwards. So if you have to start here and go there, whoops, well, then what you want to do is remember you had a catalyst. So bring in the catalyst. This time the catalyst is going to go grab the H plus because you start with negative. It's a base catalyzed mechanism. So keep your anions around. Got an anion here to start with, and I made an anion. And I got a neutral compound. That's cool. And then, hey, lone pair. There's an actual lone pair. There's 3 of them on oxygen, but oxygen prefers 2 bonds, 2 lone pairs. There's an extra lone pair here. Hey, drop that down and reform the double bond. Oh, and I can't keep this bond to the nitrile group because that would be 5 bonds here. So this bond simultaneously has to break away. Yeah, I'll just draw it this way. There we go. And that's our mechanism. You know what? There's another way though. That's the first method for remembering how to draw the mechanism of hydrolysis of cyanohydrins. The second way is, well, you already have to know this method. The forward direction, how do you prepare or form a cyanohydrin? So what you can do is draw this out on the test. Say, okay, Dennis is asking me to hydrolyze it. I know the other direction. I know the forward direction. So I'll just map this out and then erase your curved arrows. I think you need a bigger eraser. This is going to take too long. There you go. Give me the big one. So all your intermediates are going to be the same because we're reversing the mechanism. And if you know the forward direction, you can draw all these. You already have it memorized. Okay, and now you have to go backwards. So start here, and then you'll say, okay, these 2 molecules got to do something. Don't know what. Oh, yes, I do. It has to turn into these 2. Well, what's the difference? Well, this hydrogen's missing. Oh, wait, it goes here. The cyanide, CN, doesn't have an H, but afterwards it does when we go backwards. Starting here, going there, the H moved over there. So let's show that with the curved O. Hey, lone pair, go grab that H. And then we made these 2 molecules. Okay, now take these 2 molecules and turn them into these 2. Oh, let's see what happened here. We have the single bond at O, and then we get a double bond at O. The HCN, hey, the H is gone. Well, is that really what's happening? On the molecule, there was a CN here. Now it's over here on the side. Okay, so it's this molecule turning into these 2. And we're going to break this bond and put this lone pair. This lone pair used to be these 2 electrons in that single bond. And where did the double bond come from? The lone pair dropping down to form that double bond. and we're done. And then if you want to check and see if they match, they should. Can you get them both on the screen? Yeah, actually, let's close this. So I got start here, lone pair pulling off H plus. Start here, lone pair pulling off H plus. Yay. Middle step, drop down the lone pair to make a double bond, kick out cyanide. Yep, that's what we said before. And this is the final product. Yeah, those are the final product. Cool. So two ways of doing the mechanism if you have to hydrolyze. I advocate the second way. You have to know the forward direction. So draw it out, erase your curved arrows, and then just logically figure out where do I put in arrows so I can change these things into these things. Cool. All right, I think, let me double check. We done with cyanohydrins? Yes, yes, we are. Cool, all right. Now let's talk about amines. That is one of the functional groups you had to memorize way back last semester. I think I'm in the wrong color. Let's switch ink. When we had to memorize functional groups, you had to memorize amine, and that's a carbon-nitrogen double bond. Okay, so if you start with acetone, which I said I'm going to stick with, to make an amine, all you have to do is, hey, wherever you have a C double bond O, make it a C double bond N. Cool. Oh, wait. How many bonds does nitrogen? How many bonds does nitrogen prefer? Honk tells us 3. It only has 2. Okay, so there's room for another bond, and they are to some carbons. I'll put 3 here. Okay, and then compare and contrast. Hey, where does this nitrogen come from in those 3 carbons? They came from the reagent. And nitrogen here is supposed to have 3 bonds. It only has 1. Well, give it 2 H's and you're done. And if you're wondering, well, where do those 2 H's go? They paired up with the oxygen to form a water molecule. So to make an amine, to summarize here, you always start with the primary amine, right? So if you talk to the nitrogen, say, hey, nitrogen, how many carbons are you directly attached to? This nitrogen says 1. I am a primary nitrogen. Other students focus on the fact that there's 2 H's on this end. That also identifies as a primary amine. Turns out you can use ammonia, right? So if we start with acetone and use ammonia, you make a double bond N to amine. What's the third bond to nitrogen? A hydrogen. There was 3 hydrogens, you remove 2 of them. That's the pattern. Start with primary amine, there's 2 hydrogens, you remove both of them. Cool, that's the reaction. Technically, there has to be a catalytic amount of H plus to make the reaction go. That's something you have to remember. This one starts out looking like an acid catalyzed mechanism. So let's take a quick look at that mechanism over here. It is the longer one, right? So acid catalyzed hydration was longer than base catalyzed hydration. You start with hydronium, start with the acid, you protonate the lone pair. Then the nuclide bumps up the lone pair. And then you start using an acid base to clean it up to get your final product. If you use an acid, everything should be positive or neutral. And this is where we're going to see some exceptions. Darn it, amine. Oh, where'd it go? Go back to the amine. Okay, before I jump into the mechanism, let me make sure I haven't forgotten anything. Oh, aldehyde or ketone, right? That's what I'm forgetting. So if you want to see the reaction for aldehyde, change this to an H and you got it. The aldehyde reaction with ammonia, now you see it, right? And then you can change this to anything else you want. Want to make this some different, benzaldehyde. then you have, that's an ugly benzene ring. But anyways, that would be the product. Cool. All right, let's take a look at the mechanism. Let's do it with acetone. And just so it doesn't get too messy, let's use methylamine. And what kind of nucleophile are amines? Go back to SN2. Remember we said anions are good nucleophiles? We also had that one slogan that said, strong bases are good nucleophiles, and SN2. S stands for sulfur, N stands for nitrogen. Good nucleophiles are strong bases and SN2, sulfur and nitrogen. Yeah, here's nitrogen. It's actually a good nucleophile. Like hydroxide ion, which is a good nucleophile, we immediately bump up the pi bond. So it looks like we're starting out as a base catalyzed mechanism. I know just a minute ago I said it was acid catalyzed because it's a mixture of both. We had a catalytic amount of acid. Ugh, annoying. This is one of the exceptions. But maybe I should make the case. You need to know both acid catalyzed and base catalyzed mechanisms to get through the imine reaction. Okay, in the first step, the good nucleophile bumps up the pi bond. Nitrogen, you keep all your atoms. And that gives you 4 bonds. And now we're violating that other pattern we talked about. If it's a base catalyzed mechanism, our intermediate should be negative. Hey, wait, this nitrogen is positive. This intermediate is both positive and negative. Nature. Okay, so imine is one of the more common. Imine mechanisms are a little bit more common than the other ones. Okay, it also helps to know where we're going. Where are we going? We're trying to change the O to an N. Hey, N, you keep your carbons. Okay, so keep the methyl group. That's the product. Put that in parentheses. Keep your eye on the prize. So that's going to help. We need to make a double bond to this nitrogen carbon, and we have to get rid of the O. So sometimes students say, well, I'm just going to break the bond now. Get rid of the O. If you give this you get this bond to the oxygen, you make the oxygen a -2 anion. Oh my goodness, that's a powerful base, very unstable. It doesn't happen. We actually need to change this into a water molecule so it can leave a little more freely. That means this oxygen needs some H's. And this nitrogen, it's making too many bonds. It needs to get rid of an H. So there's 2 options here. The shortcut is just do a proton transfer. It's an acid-base reaction where you just say, hey, this carbon's tetrahedral. The bond angle is 109.5 between the O and the N, right? There's the center of the carbon, of the molecule of carbon, connect the O, carbon connect nitrogen. That bond angle is 109.5 approximately. And with this hydrogen sticking off the nitrogen, there might be enough room for the lone pair on the oxygen just to grab the H+. Opposites attract, negative and positive. That might actually happen. So I allow students to do this shortcut. And now our compound is neutral. Other textbooks. So I'm putting this in parentheses, saying it's an alternate mechanism, alternate steps. So if you Google the imine mechanism, you might actually see this. And if this is the one you got memorized, I'll accept it also for full credit. Start again with this, same intermediate. And then we talked about catalytic amount of acid. You can start with H+. You can actually breathe on this, put a little moisture from your air on that, or the solvent you're using might have a little bit of contaminating humidity, water from the air. Wait, now we want hydronium. We don't want a base. Yeah, and there's something I haven't talked about that I probably should have mentioned. A little bit higher. Sometimes a catalytic amount of acid is required. I believe the ideal pH is between pH 4 and 6. If it's too low, the acid will actually attack your amine. Amines are weak bases. So if it's too acidic, the amine gobbles up all the acid. And then the lone pair, there is no lone pair available to bump up the pi bond in step 1. So you can't have too much acid. And if it's too basic, then you can't move on from this step, I think. Yeah, if there's too much base around, it moves the H+, this is neutral and that stays negative and then dies. So you need a catalytic amount of acid. Again, this is the alternate mechanism. Lone pair grabs H+ from the acid catalyst. The nitrogen's still positive, making 4 bonds down here, but we make water. And now we have a weak base that'll grab that H+ from the nitrogen. And you start with acid, you end up with acid. And you went to the same intermediate in 2 steps. Some people favor this just because they're worried about that angle being too far apart. And actually, this is sort of like a proton transfer twice. Acid-base reactions are very quick. I actually don't know which one's happening more often in solution. Both are probably happening. Anyways, let's move on because there's no imine yet. Now remember, we had to get the oxygen to leave as water. So now it's time to bring in that H+. And if you're doing it the alternate method, you already have the H+ ready, right? So you have this intermediate with hydronium. I got the same intermediate. Add H0+, and I want this to be water. So lone pair on the oxygen, go grab an H+. There we go. And then we got a water molecule. And then we want the water to leave. So we want this bond to break. That would make a carbocation, but we don't get carbocations. Carbocations can rearrange, right? But what else do we want? We want a double bond to the nitrogen. So hey, lone pair, why don't you drop down your lone pair like oxygen did before to make the double bond? Remember in the cyanohydrin formation mechanism? The oxygen had a lone pair, used it to create a double bond. Nitrogen's following that same pattern. Okay, now choices. If you choose to draw your resulting molecule like this, because that's how the angle is, I give you full credit. I'm gonna put that in parentheses because that bugs me. This is one crazy bond angle, right? As the water leaves, this carbon is gonna allow these methyl groups to swing up above. So then if it becomes a 120 bond angle, since it's sp2 hybridized now, hey, that center carbon making a double bond, it's sp2. And 4 bonds, 1 to methyl, 2 here, double, and the 4th one to the hydrogen. Yeah, we're good. Cool. And then we kicked out this water molecule, so it's also there. And like what we saw before in the hydration reaction and in the cyanohydrin formation, come on. Let's see if I keep it on the screen. Nope, it's too long. We also have to clean this up at the end. So water, get rid of that extra hydrogen. I'll put it down here so there's a little more room. And we finally get to the imine. And it's drawn upside down, but who cares? If you want to draw it the other way, you can. The water molecule picks up an H+, we reform the acid catalyst. There we go. Down with the mechanism. Cool. Let's see. The mechanism is also reversible. You reverse it by adding hydronium ion. Excess of water, really. So this is an equilibrium reaction. I should put double arrows, equilibrium arrows on all of these. I'm not, well, I am right now, but on my normal exams or answer keys, I usually don't. Whoops. but in nature, it's all reversible reactions. So if you add excess primary amine, you drive the reaction to right to form the imine. If you add a whole bunch of water, here's the water being added, you then drive the reaction to the left to get rid of the water you added, and you favor the hydrolysis product, the ketone, or the aldehyde, right? Just add an H here. We need the word hydrolysis. Oh, right there. The reverse reaction is called hydrolysis of amines. So we're going to be hydrolyzing a lot. Nature does it all the time. I'm thinking about the digestive process. We digest carbohydrates, and that's actually a hydrolysis reaction in part. We digest proteins. That also begins with hydrolysis of amides, actually. And hydrolysis is formed from two words or two roots. Hydro, referring to water, hydration, water. Lysis means to cut. So hydrolysis literally means to cut with water. I never thought water was sharp, but it cuts molecules in half. So what we're going to do is we need to know the reverse reaction. We're going to start with an imine. Start with an imine and reverse the mechanism. Use the hydronium ion and go back to the ketone. We're going to cut right here with water and add an O from water here to make our ketone, and add the two H's from water to make the primary amine. All right, let's see that mechanism. And again, there's two ways of doing it. One's to memorize it, hydrolysis, and just memorize everything the way you memorize your mechanism. But what I really encourage you to do is memorize the forward way, and then just reverse your reactions, erase your arrows and reverse it. Okay, so sample problem. Show the mechanism. Let's try something different. Let's draw this. And if we're going to hydrolyze it, we add hydronium ion. Okay, so if you see this, then you might say, okay, wait, what the heck is this? Did we go over this reaction? I'll start by identifying the functional group. C double bond N. Oh yeah, that's an amine. How do you make an amine? You make an amine from a primary amine and an aldehyde or ketone. And how's the pattern work? Well, wherever there's a double bond O, you then get a double bond N. Okay, but now we're going to hydrolyze it. So wherever there's a double bond N, you're going to get a double bond O. So what I would encourage you to do in your answer, step 1, show the mechanism to synthesize, to make, to form amine. And the pattern was wherever you had a C double bond N, you used to have a C double bond O. That's really ugly. We need to do better. And then, so these two carbons are double bond to oxygen. The nitrogen here started with an ethyl group. The nitrogen started with an ethyl group. Oh yeah, and two hydrogens. And the mechanism is go bump up the pi bond, two arrows. Everybody keeps your atoms, and all we're going to do is link the nitrogen to this carbon. That's what that curved arrow is saying. Hey, use those two dots to make this bond. And then this pi bond, shove it up on the oxygen as an extra lone pair. So maybe The visual learners will appreciate. Let's put in the 2 original lone pairs. And the new lone pair came from this pi bond, those 2 electrons. Okay, then what? Well, you got opposite charges. That doesn't look stable. Let's neutralize the molecule. The shortcut is, hey, negative, attract the positive. Literally, lone pair, go grab that H, or one of the hydrogens. And notice where there was 2 hydrogens, now there's only 1. Everybody's happy. If you want to draw on the lone pairs, we got them. It's all neutral. Wait, what are we trying to do? We're trying to make a double bond the end. Oh yeah, we need to get rid of this O. Don't break it away as hydroxide ion now. That's powerful base, bad leaving group. You need to form water. Okay, how do I get another H on this oxygen? Oh yeah, the imine reaction requires a catalytic amount of acid. So bring in some hydronium ion, the source of H+. Make a water molecule here. And now it's ready to go. So break it away. But wait, don't make the carbocation. Hey, nitrogen, time for your double bond to form. Try to keep this on one screen. So nitrogen, make your double bond. You have the ethyl, you still have the hydrogen. So you're making 4 bonds. Positive charge on you. This carbon is now double bonded. And it had, whoops, not this last bond. That one broke. And we formed a water molecule. We're almost there. My imine looks pretty close, but there's 4 bonds, positive charge. We need to get rid of that positive charge and a 4th bond. Let's get rid of the H. Get rid of the H+. So water, will you please help me out? Sure, go grab that hydrogen. There's the imine, there's the hydronium ion, and we're done. We made this molecule. Oh, wait. That's not what we wanted. We want to start here and go back to here. We want to start with the imine and hydronium. Yeah, the imine and hydronium, and then we want to reverse our reactions. So where's my eraser? So erase my arrows. Yep. So on the exam, you can certainly do this. I encourage you to work in pencil on the exam so you can erase things. Good. And then let's see. Am I missing something? Yeah, one more. Good. All right. Go give me a pen, pencil. And then, whoops, I'll mark up the screen. Why? All right, and then say, hey, we're going to start here. And go backwards. And here. So that's our product of hydrolysis. You reform the aldehyde that was originally used. You start with the imine, that's what the question says. So how did these 2 molecules turn into these 2? Well, hydronium is missing an H. The nitrogen gained 1. Oh yeah, lone pair, go pick up H+. That was step 1. Now these 2 molecules turn into these 3. What's going on here? Okay, wait, that's extra. All we're going to do is connect this water. Here's an O with 2 H's, O with 2 H's. Want this lone pair to hit here, bump up the pi bond onto nitrogen. And then that means this nitrogen has a lone pair. Ethyl, hydrogen, good. Only 1 bond there, good. And the water molecule is now attached. Oops, look at this. I forgot to erase a curved arrow. I'm glad I changed ink. That was easy to point out. Okay, give me the pencil. Okay, so now you gotta change this molecule to this one. It's just missing this H. Oh, the water molecule picked up the H. There you go. So lone pair on the water. Can you go grab one of these things? One of those H's? Sure. That turns the water molecule into hydronium. This oxygen then loses an H and the plus. Cool. Now this thing's got to turn into this thing. We're missing this H on the oxygen. The nitrogen picked up an H. Oh, hey, nitrogen, go grab yourself an extra hydrogen. No problem. Got it. Now what? I go here. Ooh, that's a big change. The nitrogen with the 2 H's and an ethyl. Nitrogen, 2 H's and an ethyl. Oh, this bond just breaks. And where's it go? Down here on carbon, up on the nitrogen. Well, right now, nitrogen's got 4 bonds, no lone pair. Afterwards, it has a lone pair. Yeah. Where those 2 electrons come from? This bond. Those 2 electrons in a covalent bond, right? 1 line equals 2 dots. 1 covalent bond consists of 2 shared electrons. Oh, but if that bond breaks, that's going to create a carbocation. Oh, wait. We're going to ask oxygen to drop its lone pair at the same time to create a double bond. There's our mechanism. Nice. It really helps, though, if you know the forward mechanism first, and then just logically reason it out to put in arrows to go backwards. Sweet. Let's see, anything else about amines? Maybe a biological example? Yeah. In biology, amines are often called Schiff bases. I actually worked on Schiff bases in graduate school. That's kind of cool. Yeah, I did. What else do we know about biology? Oh, helps us to see. Amines are important for night vision, also day vision, but more important in night. So let's take a quick look at that. I got this other handout on Canvas. You can look at it at your leisure if you want a little more detail, or pick up a biology textbook, or go on the internet. But anyways, quick little rundown of amines that help us to see the chemistry of vision. You've seen the eyeball before, at least diagrams of it. The back is the retina. Within the retina are rod and cone cells. Rod cells help us see black and white, contrast and intensities of light. Cones help us see color. C for cone, C for color. We're going to look at the rod cell. So within the retina, let's inspect the rod, zoom in on that. So here we go, a rod cell over here. Lots of those stacks of within these discs. Go within a disc, and within the membrane of the disc, we can see this protein here. And found within that protein is this molecule here, retinal. Yep, that helps. Al ending aldehyde. We have an aldehyde here at the end, right-hand end of the molecule. The protein's called opsin. When it binds retinal to an imine, we'll see in a second, you form the protein called rhodopsin, and that helps us to see light, at least in the rods. And the key physics behind vision is light comes in, and the light's absorbed by this conjugated set of pi bonds. We learned about wavelengths of maximum intensity being absorbed by conjugated pi bonds last semester. And the energy of the light is then used to temporarily break the cis. Where's the cis? This one right here. Identical groups. The 2 H's are on the same side of the double bond. That actually gets broken. It rotates to form a trans double bond. This one here, right? We have the aldehyde double bond, then this one's cis. Aldehyde double bond, then this one's now trans, and trans is much more stable. Cool. And what happens physically in the protein is this molecule straightens out. That's a physical shape change, conformational change. and that's detected by the protein. So right here, if we zoom in on this blob, that's still the opsin protein, and now it binds to an imine. On the protein, there's a nitrogen, a primary amine, reacting with cis-retinal, an aldehyde. Aldehyde and primary amine form an imine. And then light absorbs, it gets absorbed, the cis changes to trans. There's a signal, opsin says, whoa, we changed that shape. The signal is sent to the brain saying, hey, right here at this part of the retina, we saw some light. Go and construct a picture from all the different areas of the retina that absorb light. Hey, but we like to see light again. So now we got to get rid of the trans and go back to cis. And it turns out in the daytime, you can do that. Where is it? There it is. Enzymes energy can switch it back and forth. And at night, if you don't have that light to help you switch it back, I think it's UV light, you can hydrolyze the imine. So you have the primary amine still in the protein, and you can take the trans retinal out, and you can bring in the cis retinal and reform the imine. It's reversible. And then that helps you to see again. Cool. Neat stuff. Okay. That was imines. I've got everything covered. Let's take a look at enamines. Might say that looks like a made-up word. Yeah, it pretty much is. Okay. An enamine has an ene in it, an alkene, a C double bond C bond. And then it also has an amine, which is a nitrogen, and you don't have a C double bond O next door. The nitrogen can have 3 carbons, 2 hydrogens, or 1 hydrogen, whatever, lots of combinations. We got both, and they connect together. So you're going to have a single bond nitrogen attached to an alkene carbon. Cool, that's an enamine. You get enamines from aldehydes and ketones. We'll start with acetone again. And this time you have to use a secondary amine. So let's bring in a nitrogen with 2 ethyl groups and a hydrogen. And what's the pattern? Well, for an imine, that's where I always go to. I said, well, if this is a primary nitrogen, what would happen with an aldehyde or a ketone? Oh yeah, wherever you have a double bond O, you then have a double bond N. Oh, but nitrogen, you get to keep your carbons. So this would be the imine. And that actually forms during the mechanism. But wait, Hunk would say nitrogen should only have 3 bonds. It's making 4, which is allowed, right? We've seen ammonium ion, the ammonium ion with 4 bonds, positive charge on nitrogen. So they exist, but it's not the most stable structure. So what happens is that this has to isomerize. And what happens is this carbon is double bonded in the imine. It stays double bonded in the enamine. The nitrogen keeps its carbons. It had 2 ethyls, stays with 2 ethyls, but in an enamine, the nitrogen connects to the carbon with a single bond, and the double bond goes to either side. Now, for my exams, I'll make it a symmetrical aldehyde, or aldehyde doesn't matter. There's only 1 carbon if it was, right? Let's try that again. Let's make an enamine with acetone. Oh yeah. Start with the imine, and then isomerize it. Put the double bond wherever you want, right side or left side. Oh, but now I want to see it with an aldehyde. Change it to a hydrogen. And you can't make a double bond across the carbon-hydrogen bond, right? Hydrogen only makes 1 bond. So double bond has to go there. So on exams, I'll either only give you aldehydes or symmetrical ketones. Symmetrical meaning that we're playing symmetry. So it'll be correct for you to choose either side of the double bond. Hey, chem majors, you'll need to know this in the future. If you don't have a symmetrical ketone, like this, one side will be more crowded than the other, and the double bond goes to the less crowded side. That's called Hofmann's rule. The least substituted alkene is preferred. And it's just a steric argument. It's getting crowded in the mechanism. I'll try to remember to point it out why one side is favored, the less crowded side is favored. That's to do with the base attacking a hydrogen. Anywho, for the rest of us, don't worry about this. You just pick one side of the double bond, sorry, one side of the carbon to make a double bond. And if it's aldehyde, there's only one carbon on your aldehyde that could possibly make a double bond. So that's where double bond goes. Anything else? Nope, we're good. Okay, good news, bad news. Bad news, enamine mechanisms are a little longer than imine. Good news, it's by one step. Just do the imine reaction and then add one more step. So you might want to pause the video and go back, I think it was up. Go back and just really understand the imine mechanism, because we're just going to do it again. Here we go. So now we're going to do the mechanism, which we have to know for exams. Start with the ketone, and I'm going to simplify it and just add dimethylamine. Okay, and we're going to pretend this is primary, even though it's secondary. Pretend it's primary, and we're going to make an imine. Okay, so the product is going to be wherever there's double bond O, make a double bond N. Step one: acid or base catalyze. Well, amines are good nucleophiles. SN2. Strong bases are good nucleophiles, and SN2, sulfur nitrogen 2. Lone pair on nitrogen, bump up the pi bond. In a base catalyzed like mechanism. All we're going to do is use lone pair to connect to this carbon, move the bond up, keep all the atoms where they started. 3 carbons, 1 O, 3 carbons, 1 O. Nitrogen had 2 methyls, and it has this hydrogen. Hey, nitrogen, you're making 4 bonds, you're positive. Plus and minus same molecule, that doesn't look right. Yeah, let's neutralize that. Lone pair, go grab that H. Cool, everybody's neutral and happy. Lone pair on this nitrogen. All right, what's our end goal? We need to make the imine and then the enamine, but we're thinking imine. Wherever there's a C double bond O, we need a C double bond N. I mean, this O's got to get out of there. There's no oxygen left in the enamine or in the imine. It has to leave as water. Ooh, this is short 1H. So go grab an H from that catalytic amount of acid. And then I like moving this H to the left-hand side, putting both of them over there, and now it physically looks like a water molecule. I like that. Hydronium turned to water. Okay, water you can leave. Oh yeah, at the same time, ooh, let's form the imine. Make that double bond. Nice. And I'm gonna swing the methyl groups up just because it's one of my pet peeves. I like to see the right bond angle here, or at least a close approximation to it. And now this nitrogen is making 4 bonds. That was why I elected to draw in the lines. You don't have to. When you're drawing molecules, draw them how you want to. If you just wanted to draw lines here the whole time, dimethylamine, dimethylamine. You can draw it that way too. This water molecule left. Cool. Okay. If we were doing an imine, there would only be one methyl group. One side would have a hydrogen. The water would pick off that H plus. Nitrogen would have a neutral charge and we'd be done. Water's like, hey, nitrogen, where's your hydrogen? Nitrogen's like, nitrogen, don't you prefer 3 bonds? Yes, please. Okay, water needs an H plus with somewhere. Just to re-emphasize that. Here it is. Way over here. There it is. Water molecule is going to grab that extra H plus, right? If it was if it was methylamine, primary amine, there would have been an H here. And the water molecule can pick it off and form the imine, we'd be done. But if it's a secondary amine, the water molecule is frustrated. It's like, there's no hydrogen on that nitrogen. You know what? There's one over here on this hydrogen, on this carbon. There's also one over on this side. Pick either one. And now it sort of looks like an E1 mechanism or E2. Let's put my arrow in, see whether it's E1 or E2. Weak base, maybe that's a helpful thing. It looks like, sorta, is that a word, sorta? Sort of. The lone pair on a weak base grabs a hydrogen, and these bonding electrons form an alkene, a double bond. That's what E1 elimination reactions do. They form alkenes. And then a leaving group is not really a leaving group. The pi bond leaves to form the lone pair on the nitrogen. And we have our enamine. And the water molecule got its H plus. We reform the catalytic amount of acid, and we're done. Cool. Yes, you can hydrolyze it. I think in the homework, yes, there is a homework problem. Not in this lesson, but the following lesson where you have to write the mechanism. It's just one extra step. I'm going to save a little time in this video and not show it here. But if you have questions, post a question on the discussion board and one of your classmates or myself will answer it. Let's do another sample problem though. Let's draw the products. So if we have this molecule, that's a legal question to ask on the exam. I should have started with one other one, but nope, we're good. We can figure this one out. Okay, so what do you do? Well, what is this molecule? What functional group is here? Well, it's got a tertiary amine. Nitrogen making bonds to 3 different carbons is tertiary. There's an alkene in here. Hey, there's an alkene and an amine, an alkene, amine, an enamine. Yeah, there's an enamine. How do you make an enamine? Enamine comes from a C double bond O, aldehyde or ketone, or ketone, and a secondary amine. Yep. Also in the mechanism, form the imine. So that C double bond O plus a secondary amine is going to look like a C double bond N. Those are the 2 things I remember about enamines. And so I look at this molecule and say, well, the enamine in the mechanism, it formed an imine temporarily. And you can scroll up here and just see it. There it is, right here. Here's my imine intermediate. I got a C double bond N in here. It's not the final product, it's just an intermediate. So where's my double bond? It's over here. It's on this ring. So these 2 carbons of the other ring were never double bonded to the nitrogen. The closest pi bond identifies a carbon that used to be double bonded to nitrogen. So here's my alkene, but the double bond, the closest carbon, that one, used to be double bonded to the nitrogen. And now nitrogen is making 4 bonds. So this is the imine intermediate. And in the last step of making the enamine, water picked off this hydrogen here. Anyways, that's a key step if you're trying to draw the products of hydrolysis. The closest pi bond that identifies the carbon that used to be double bonded, and now cut it. Wherever there's a C double bond N, you used to have a C double bond O. And the nitrogen is over here. Wait, nitrogen, you need 3 bonds. Yeah, put a hydrogen on it. And now we have our secondary amine. And we have our ketone. And more importantly, we get all the points because that's the right answer. So remember, when you're hydrolyzing, we're cutting with water, hydrolysis reaction. And so you want to cut right there. Separate the C double bond from the N. Keep the double bond on the C so you can put an O on it. Get your aldehyde or ketone back. Nice. Okay, I know this video is getting long. So next one, we're not doing a mechanism. And it's not because the mechanism, I'm sorry, it's not because the video is long, it's because the mechanism is long. And you can figure it out if you need to, but no one asked this on organic chemistry. So no mechanism for this one. It's actually a variation of the imine reaction. You're going to take a special amine, this hydrazine is the name of this molecule. We have two, it kind of looks like 2 ammonia molecules fused together. That's hydrazine. It's actually a form of rocket propellant. So be careful with that stuff if you use it. And you add hydroxide ion. Those are your 2 reagents. And it's very specific for aldehydes and ketones. This is the unit of aldehydes and ketones. So unfortunately, later when we talk about in unit 3, carboxylic acids, esters, amides, students will see that C double bond O and try and do a Wolff-Kishner reaction on it. It's like, ooh, wait, no. Wolff-Kishner is in the unit 2 aldehyde and ketone unit. Doesn't work on carboxylic acids, esters, and amides. So let's emphasize that by drawing an ester. You know what? And some pi bonds. Let's just get some more pi bonds in here. And we've got a ketone here. And we'll put a ketone here. And then we'll put a pi bond there. Why not? And we'll get a nitro group in here too. Just so we can refresh our memory on some other stuff we've seen earlier in unit 1. So little hydrazine, which could be written this way, right? You can write H2NNH2, but there's 2 N's and 4 H's. You write OH minus, or commonly what you see is KOH with hydrazine, sometimes written that way. So just, yeah, it's all the same. Sodium hydroxide works too. I think potassium hydroxide is more soluble to hydrazine in whatever solvent they use. Ethylene glycol, maybe? Putting that in parentheses. 2 carbons, ethylene, 2 alcohols, that's weird, on separate carbons. Ethylene glycol is a common name. Anyways, reagents drawn this way or that way. Sometimes with a solvent, I leave out the solvents as a rule of thumb. Unless it's an SN2 reaction, I might use my polar A product solvents. If it's hydrazine, it's a Wolff-Kishner reaction, at least in the first level of organic chemistry. Okay, so what happens? Aldehydes and ketones get eliminated. So let's copy the molecule, take out the aldehydes and ketones. Well, there's a C double bond O here, but it's an ester, so it survives. There's some pi bonds here, they survive. Within the nitro group, Remember, there is a double bond O. That's the lowest dot structure of nitro, but that's not a ketone aldehyde. It's a double bond O, not a ketone aldehyde. It's nitro. There's a ketone right here, so it's gone. Technically, you replace it with two H's. And there's a second one right here. It's gone too. This pi bond survives. Compare and contrast. Draw the same molecule. Whoops. O2 is nitro. Couple of ketones. And let's hit with hydrogen gas and palladium, or palladium and carbon. Back in Unit 1, we said, oh yeah, hydrogenation attacks alkenes, aryl halides, aryl ketones, aryl aldehydes, double bond O's next to benzene rings, and the nitro group. That leaves esters alone, though. So ester, you survive. Even though you're a double bond O attached to benzene, doesn't count. That's not an aryl ketone, it's an aryl ester. The nitro group becomes an amine, form of aniline, if that's the parent. I don't think it is, but don't worry about it. Double bond O, oh yeah, that goes away. It's eliminated. But other ketones survive hydrogenation, but not the alkene. There we go. That's Wolff-Kishner for you. Anything else I need to put in here? Not in terms of anything in terms of mechanism. No mechanism, no other reaction. We're not going to reverse this one. And the reason for that is the hydrazine turns into nitrogen gas. And then nitrogen gas bubbles away. Nitrogen is really stable, and so the reaction is not reversible. Cool, we're done with the Wolff-Kishner reaction. Oh, I guess I should just point out, there's two ways of removing the ketone. If you only want them activated ones next to benzene ring, you selectively remove this one and not that one. That one survived. That's kind of cool with hydrogenation. If you just want any ketone, whether it's next to benzene or not, they both can get eliminated with the Wolff-Kishner reaction. So you got choices. Cool. Last reaction. Ooh, yes. Acetal formation. Where'd you go? Must be down below. Oh yeah, way down here. Get all the information on the screen in one shot. Ooh, I saved perhaps the most important reaction for last. Or maybe someone else will argue, wait, chemistry vision is kind of important. So maybe imines are really important. And knowing them help us understand enamine mechanisms too. Yeah, it's all important. Acetals and ketones are found in carbohydrates. So that's going to make them pretty important as well. So if any of you are biochemists, pay attention to this reaction because you'll be looking at carbohydrates in your near future. So I'll pick this ketone, but it could be an aldehyde, put an H here. And what you need are two alcohols. So I'll just use methanol. The organic chemist usually doesn't balance in their reactions, but there should be a 2 here if you want to balance it. And you need a little bit of acid, catalytic amount. So sometimes you'll just see, maybe you see the 2 H's. I'm sorry, the 2 alcohols listed. You might just see H+, you might see CADH+, catalytic amount. Lots of different ways. You might see CADHCl, and then you'll just see the solvent. And wait, that's not all, only just the solvent, protic solvent, it's actually the reagent too. So lots of different ways of writing it. But if you see alcohols react with aldehydes, ketones, you're going to form an acetal. An acetal, or a ketal, what you do, it's very similar to hydration. Scroll back, take a quick peek at hydration. Keep going. That cyanohydrin, hydration. There we go. What do we do with hydration? We took a double bond O and split it into two alcohols, whether it was acid catalyzed or base catalyzed. Which one is our acetal reaction most similar to? Acid catalyzed, right? We have a catalytic amount of acid. So in hydration, acid catalyzed, lone pair picks up H+, the weak nucleophile water bumps up the pi bond, and then a water molecule neutralizes the molecule. You get a pair of alcohols where they used to have a double bond O. We're going to use that same pattern and do it twice for acetals, if I can find it. Okay, so give me the cursor. Come on, computer. There we go. Wolff-Kishner and then acetals. Okay, so where we have a double bond O, you want two single bond O's. So this carbon used to be double bonded oxygen. Now it's single bonded to two O's. Where do these two O's come from? The two molecules of the alcohol. So oxygen, A new oxygens, you keep your carbons. That's what the imine and the enamine reactions did. The nitrogen kept its carbons too. So that's nice. Pattern's consistent. Oh, and we're done. That's your acetal. For those of you who are curious about balancing things, you start with one O over here, you bring in two O's here. That's three O's, where I'm missing an O. And then 1, 2, 3 carbons, 1, 2, 3 carbons. Take away this O. I have two methyls. Yeah, I see the methyls. Two O's. Wait, there's two H's. Two H's. Yeah, I also make a molecule of water. And guess what? This one is reversible. So if you add more water with the acid catalyst, you reverse it and go back to the ketone or the acetal. Sorry, the ketone or the aldehyde. Brain's trying to do two things at once. Technically, here's the second thing my brain was trying to do. You started with a ketone. So technically, this product should be called a ketal. But chemists are kind of loose. I know I am with their logo, with their jargon. I still call it an acetal. Although, if you start with the aldehyde, you definitely have the acetal. Cool. All right, mechanism. Definitely know the hydration mechanism for acid catalyzed hydration. That'll help you get through this one. We'll do the mechanism in a second. Let's see if there's something else I need to know. We pointed this out. Carbohydrates, we pointed that out. Oh yeah, this is helpful. You'll need it in Unit 5, and there might be a homework problem or another. Oh yes, actually, you do need this. Here's the key. Wherever there was a double bond O, you now have a carbon linked to two O's. You actually have two ethers with a common carbon. Right? So let's look at this ether oxygen. It's linked to two carbons, this one and that one. Let's look at the second ether. This O is linked to this carbon and that one. Hey, this carbon is common to both ethers. Oh yeah, that's the special carbon that used to be an aldehyde or ketone carbon. There you go. So that's the key. When you have to hydrolyze your acetals and go back to the aldehyde or ketone, to go back to the double bond O, look for that one carbon that's connected to both ether oxygens. Both oxygens are ether. That'll identify the carbon that will be double bonded after hydrolysis, after you reverse the reaction. Also in carbohydrate chemistry, they make a big deal about something called a hemiacetal. Hemi. Do you remember hearing about a hemisphere? Right? So if you have a sphere and you take half of it, maybe the northern hemisphere, half a sphere, You got half of the world. A hemiacetal is when you have half of an acetal. You don't have both ethers, you only have one ether. So a hemiacetal is where you do have two oxygens, but one oxygen is the ether, the other oxygen is an alcohol. So I'll point out the hemiacetal in our mechanism. And that's an important functional group. Hemiacetals is a functional group. Acetals are a second functional group that we need to know for carbohydrate chemistry. And we get some carbohydrate chemistry in Unit 5. And then finally, I'm going to save this one for another video. The acetal group is an excellent protecting group. So another video for that one. So let's end this video with the biological application. We'll look at some carbohydrates, but first we'll also see the mechanism. Okay, mechanism. Let's show the mechanism for acetal formation with acetone. Cool. Okay. What was the overall? Let's have our end game in sight. Overall goal. I should overall reaction. Sorry. We're going to start with acetone. And I'll stick with methanol. No, I won't. Let's change it up. Let's start with ethanol with a catalytic amount of acid. Okay, so what do? I had a student say, well, if you hold your fingers up like this, let's go to full screen. Hold your fingers up like this and think of the O on top. There we go. And then just split it and put an O on either one. That's visually what you're going to do when you make an acetal. So I like that. I'm a visual learner. So where there's a double bond O, split the double bond. And then there's O's on either end of that line. Oh, wait, these O's came from alcohol. Oxygen, keep your carbons. There's an ethyl here and another one there. Yeah. Cool. Okay. There's an H plus here. That's acid catalyzed. So what's our acid catalyzed hydration reaction? Well, we start with hydronium, right? And the mechanism could have been H plus or hydronium, your choice. If the reagent's given one way, your mechanism, you can switch it to the one you're more comfortable with. It's the same thing, same source of acid. So in hydration, strong acid reacts first, H plus. The lone pair, go pick up the H plus. That activates the carbonyl group, makes it more reactive towards a weak nucleophile. Alcohols are weak nucleophiles. So is water. Need some help, need some encouragement. So in hydration, a water molecule bumps up the pi bond. In acetal formation, it's an alcohol that bumps up the pi bond. And oxygen, keep your carbons, but also keep that hydrogen in this step of the mechanism. Cool. Hey, this kind of resembles the imine reaction now. We actually had a negative oxygen and a nitrogen with a positive charge here. So what happened then? The oxygen uses lone pair to grab that H plus. You can take that same shortcut. I'll allow that. However, I also want to show you the hemiacetal. So the alternate step is you bring in another alcohol molecule or a solvent, or you could use water, and the solvent grabs an H plus. And now we have our ether with the alcohol on a common carbon. Here is the hemiacetal. Okay, so carbohydrates form this as actually a somewhat stable intermediate. I'll point that out in the biological example at the end of this video. The ethanol molecule, the extra solvent molecule we used, it's protonated now. It has extra H plus. So what do we want to do here? We want to go from a double bond O to a pair of single bond O's, but these O's come from the alcohol. These O's have carbon attached. This O doesn't have any carbon. So you need to leave oxygen, and you should leave as water, just like in the imine reaction. So lone pair on the oxygen, go grab this extra H+. And let's put it over here. Good. So I copied this molecule over, put an extra H+. There's a water molecule, I'm sorry, there's an ethanol molecule there. I'm gonna leave it out. Because in the next step, water, you gotta leave, but no carbocation. So the lone pair on this oxygen, just like in the imine reaction, lone pair came down, doubled up the bond. I'm gonna swing those two groups, these two methyl groups to the other side, double up the bond. Got a plus charge here because 3 bonds to this oxygen when it made the double bond. The water molecule left. And now this molecule lost its H. It's an ethanol molecule now. And what do I need? What's my end goal? 2 ethers. Well, I kind of have one. I need a second oxygen to make an ether to this carbon. Hey, let's just do this step again. Alcohol, alcohol. Bump up the pi bond. Bump up the pi bond. Good, that took care of the 3 bonds of oxygen. I like that. The alcohol molecule just came in, keeping its H in the ethyl group. This oxygen took the pi bond, made its second lone pair. It's nice and happy with 2 bonds, 2 lone pairs. And if you want to use this water molecule to pull off the H+, you can, but you had a whole bunch of alcohol to drive the reaction to the acetal. So your base is more likely to be the alcohol. But if you use water here, like we did in the imine, like we do in hydration, those mechanisms, yeah, I will allow it. And now we have 2 ethers on a common carbon. That's our acetal. Yay, we're done. And then I'm just going to be complete. This, that's a plus sign. This alcohol picked up another hydrogen, so now it's positively charged. Cool. And of course, you want to hydrolyze it. You need to add water. Ooh, that might be a good case. Maybe I should encourage you to use a water molecule here so that when you reverse it, you'll have water already, you'll have hydronium here. And then when you reverse it, you have a lone, right? This oxygen loses the H, but when you're starting with the acetone, you want to hydrolyze it. You take this lone pair and connect it to this H+ and go form water. Okay, plenty long video. Let's just see the biological example, and then we'll call it quits for now. And there's still a few more nucleophilic addition reactions for aldehyde and ketones, but we'll save it for the next video. Hey, so let's end on a positive, fun note. Let's look at some carbohydrates. Tie some stuff together. So blood sugar is glucose. It's sugar, it's a carbohydrate. One way to draw blood sugar is to show the double bond O. There's an aldehyde in glucose, blood sugar. And in the bloodstream, there's plenty of water. You just need a little acid catalyst. So water freely forms H+ and OH- in an equilibrium. So there's a catalytic amount of H+ around in pure water. And so the sugar itself, the glucose molecule, actually has an alcohol, several alcohols. One of them attacks the aldehyde and forms a hemiacetal. We got common carbon connected to an ether and an alcohol. Or it could draw this form. We have a common carbon connected to ether and an alcohol. This 6-member ring looks like the chair conformation, and it is. And we have an axial bond, or we can have an equatorial bond. Which one's more favorable? Which one's more stable? Equatorial, right? It's less crowded. And so in the bloodstream, right now in your bloodstream, some of the free glucose, that's the blood sugar going through your veins, approximately 63% of it is in the equatorial form of the hemiacetal, ether and then one alcohol, the hemiacetal. 36% is in the axial, more crowded form. That's called the alpha form. And only less than 0.5% is in the open chain form. Just because this alcohol is so close, it cyclizes and forms a nice 6-member ring. Nature likes 6-member rings. And hey, if you had a big meal, you're digesting your food, got a lot of blood sugar in the liver, you'll start storing it, the excess sugar, as glycogen. And in plants, they can store it as starch. So what nature will do is take the alpha form with the axial bond, and form acetals. One glucose connects to another glucose, all axial, or the alpha form. And we get we have acetal linkages, right? Common carbon with 2 ethers, common carbon with 2 ethers. Here's another acetal, common carbon, 2 ethers. If you go around the molecule, hey, here's an ether. Yeah, but there's not a second ether. This is not an acetal carbon. So find the carbon, link the 2 ethers. There's your acetal. Nice. This carbohydrate is called starch, using the alpha form. It's great for food, not great for building, unless you're making the volcano out of your mashed potatoes and pouring the gravy as lava. Yeah, that's about all you can build with starch. However, if you use the beta form, you can link them into acetals and you get cellulose, which is actual great building material. You can make wood, paper, and cotton. Cotton, yeah, eat this. It's made from sugar. Problem is, our bodies cannot break the beta bond here. The equatorial bond is too stable. We don't have the right enzymes, but we can break it when it's axial. So we can digest this form and not this form. And it's just an axial versus equatorial bond that makes mashed potatoes yummy. Well, I think so. Corn and wheat, but paper and wood, cotton, not so yummy. Cool. There's more here, but that was the main points I wanted to make. Thank you, and I'll see you in the next video.